All right, what I would like to do now is discuss the Hilbert transform for Fourier series. And I want to first define that and then rewrite that and the Hilbert transform for the Fourier transform in a much more digestible way that allows us to prove the LP boundedness of both the Hilbert transform for the Fourier series and for Fourier transforms. So we will only actually prove the boundedness of the Hilbert transform for the Fourier transform, really just for time reasons. The proofs are going to be very similar, actually. And as I mentioned early on, we're going to employ techniques that don't use complex analysis because those techniques can be applied to prove the boundedness of other similar operators in higher dimensions, and particularly partial differential equations. Not surprisingly, usually things are in higher dimensions, so it only makes sense, to create tools that don't just work in dimension one, or don't just work in in one complex dimension. Now, of course, regular complex analysis is useful for studying the Laplace equation and harmonic functions, but basically for PDE, that's really all it's good for. And there's a lot of other useful PDEs out there that our techniques will apply to. Okay, so first of all, remember that the goal to prove the LP boundedness of Fourier series was that we need to get a bound for Sn, the partial Fourier sum operator. So we need to prove that this supremum is bounded, where Sn, remember, we wrote as an integral operator. But for our purposes now, it's more important to recall the definition. And the definition, as I said, it's just the partial Fourier series operator. It takes an f and spits out the truncated Fourier series from minus big N to big N. Okay, so I'm going to write this in a kind of useful way, which allows us to define essentially the Hilbert transform for Fourier series. This is also sometimes called the Hilbert transform on the circle because you can think of one periodic functions on 0 to 1, or on the real line rather, as functions on the circle. Kind of the trivial identification 0 to 1, where you identify the endpoints, is identified with the circle via just take x going to e to the 2 pi I x. But anyway, and some homework will examine connections to complex analysis, and particularly to the Hardy space. Okay, so anyway, so remember, just remind you what the sine function is. Well, it's 1 if x is positive, 0, x is 0. And as I mentioned, often you don't even define it for x equals 0. For our purposes, it's useful to just say it's 0. So if x is negative. Okay, so what's this whole thing here going to be? Well, you can just check, or if you're feeling kind of lazy, you can literally graph SGN of x plus some number minus SGN x minus the same number. And you'll see that it's basically a characteristic function from minus that number to that number, at least for x strictly between that number, minus that number and that number. So particularly if n is going to be bigger than big N in absolute value, this is going to be 0. But it's really easy to check using different cases. Particularly, both of these are going to have, they're going to have the same sign, or rather, both of these are going to be either 1 or -1, and hence the whole thing is 0. And this is going to be 2 if absolute value of n is less than big N. One of them is going to be +1, and the other one's going to be -1. And hence, you're going to get 2. Again, you just check this, very easy. Okay, so what happens when n is the endpoints? Well, let's just see. When n is big N, this is 1, this is 0. So we get 1/2 here. And this 1/2 is just, 1/2 times 2 is 1. Okay. So in that case, this is just 1/2 f hat of big N. Well, to get f hat of big N, we have to add another 1/2 f hat of big N. Sorry. When n equals big N, the sum here is 1/2 f hat of big N e to 2 pi I big N x. Again, to get a 1 in front of that, we just add another 1/2 of it. Same thing when n is minus big N. This is going to be 0. This is going to be -1. Minus minus is 1. So then the sum here is 1/2 f hat of minus big N e to the minus 2 pi I big N x. Add another 1/2 of it to get 1 in front of the f hat of minus n e to the minus 2 pi I n x. Okay. Right. So let's define C, and this is called the conjugate function. Professor Zhu maybe we'll talk about this in his course. It's very closely related to harmonic conjugates and complex analysis. So we're going to let CF be basically the Fourier series, except we're going to plop in a sign n. Okay. So particularly when n equals 0, we get 0 here for the sum. The term when n equals 0 is just 0. Okay. So if you take the L2 norm squared of CF, you get the little L2 norm squared of all the Fourier coefficients except f hat of 0. So if you add that up, and this is, of course, f hat of 0, we get the L2 norm squared of f, just because this is basically the same thing as just saying, which we proved very carefully for an L2 function at least. Right, n equals minus infinity. Right. So C is certainly bounded on L2, and it's basically practically an isometry. Not exactly, but it's behaves very much like an isometry. All right, so I claim that if I can prove that C is bounded, then this supremum is also bounded. Okay. Now, at a first glance, this is not a very helpful reduction because this operator here looks almost worse than this nice integral operator. But actually, we'll see that C can be written in a very, very digestible way. Okay, so why is this true? Let's play games similar to what we did previous for Fourier transforms. Let's say Mn is multiplication by this complex exponential. Okay, so you take the Fourier coefficient, just use the definition, and you write this here very trivially as e to 2 pi minus 2 pi I little n plus big N. And so by definition, you have the Fourier coefficient with little n plus big N plugged in. Okay, so why is this useful? Well, let's unravel this definition here. So this Fourier coefficient is going to be the Fourier coefficient of whatever this is, well, little n minus big N. So instead of big N, so if I have a minus big N here, this is going to be minus. Okay. Right, so now what's the Fourier coefficient of this? Well, you can check that it's the same thing as the Fourier coefficient of whatever this is, except with the sign. Okay. So, right, and we're plugging in little n minus big N into that. So it's sine little n minus big N times the Fourier coefficient of this here, little n minus big N. Okay, well, this has the effect of just adding big N into the Fourier, into whatever you're dumping into the Fourier coefficient. So this is really going to be n minus big N plus n, which is little n. Okay, so we get sine little n minus big N f hat of n. And similarly, if you have a positive here, a minus here, this is sine little n plus big N f hat of n. Okay. So 1/2 of this operator here is going to be this sum right here. Okay. Just from what we did here. We computed the Fourier coefficients. So, right. Okay. Right, and just remember what C. Right. Sorry. So, right. We're going to. All we're doing is we're at least when f. So let's say f is an L2 of 0 to 1, and it should be an x here. Sorry about that. So if f is an L2, we just write out the Fourier series of this whole thing. We computed the Fourier coefficients. And these are the Fourier coefficients, so this is a Fourier series. Okay. Well, this is basically the same thing as Sn of x, except we have to subtract off these kind of endpoint terms here, right? Or rather, this whole thing here, this is a little confusing, this whole thing here plus this whole thing here, forget about this minus sign here, Sn of f of x is going to be this here plus this here. That's exactly what we had right here. Sn of f of x is going to be this sum here plus these two n terms. All right? For the purposes of boundedness, these terms here basically they're meaningless, basically. Because, right, so if I have, let's just do this one here. Take the absolute value, e to 2 pi I n x. Well, this is just bounded. So actually it's equal, so I'll get rid of that. And we've done this before by Holder's inequality. Sorry about that. By Holder's inequality, this is less than or equal to the LP norm over 0 to 1 of f. And same thing here. And also because mn is just multiplication by this complex exponential, which has modulus 1, mn is trivially an isometry on LP, so the operator norm is equal to 1. Okay, so let's put all this together. So the operator norm for Sn, so first of all, Sn, remember, is bounded. By Holder's inequality, you get a fairly trivial bound but in terms of n, and that's no good. We want to eliminate the n dependence. But we do know it's bounded, so we can take the operator norm over a dense subset. Particularly, let's take it over S, where S is going to be the finite linear combination of S is just the span of all these complex exponentials. Okay. So S is just a set of all finite linear combinations of these exponentials. For n, sorry, that should be n is an integer, not a natural number, but n is an integer. Okay, so by Fourier's theorem, this is dense in LP. Okay. So because we already know this is bounded, and maybe I'll make this as a little homework to make sure that we're all on the same page here. But because Sn is bounded on LP and S is dense in LP, we can write this operator norm in the following way. Okay. Well, from what I just talked about a moment ago, this is bounded independent of n by CF and LP norm plus 1, at least when you take the supremum, because, you know, this is obviously invertible. And trivially, this takes S to S. I mean, if you multiply, you have a finite linear combination of complex exponentials, you multiply that by another complex exponential, you still get a complex exponential. There's nothing really to that. You just change the integers, you just shift the integers. But anyway, okay, so the key thing to do now is, what is CF? Answer the question, what is CF for F in this set here? And the point here is that when we try to do things like interchange sums and integrals, and you know, we're not going to run into any technical problems if we're dealing with nice functions. And this is really, for our purposes, as nice as you get. And I just call this S because this is going to play the role of the Schwartz space when we talk about the Hilbert transform more on the real line, which we'll do in like 10 minutes. Okay, so let's do something that you often do. Okay, so first of all, I should mention that there is no pointwise issue. Let's just, so remember here, let's just remind you what CF is. N minus infinity to infinity. Hopefully I can fit this in. So this is going to be important in a moment. So first of all these are 0 except for a finite number of integers. And that finite number of integers is the same integers that F, you know, it's the frequencies involved in F. F is just a finite linear combination of these complex exponentials. If you're away from any of these n's, and when you write that sum, the Fourier coefficient is 0. So this infinite sum is really a finite sum. So despite that, it's going to be useful to consider this regularized version of CF for R between 0 and 1. So one really interesting thing you'll notice is that this is really an operator, essentially it's an operator for complex valued, or an operator on the disk. Why? So let's say Z is R e to the 2 pi x. So we're saying this is in the unit disk. And that's obviously the same thing as saying r equals 1. So z to the n. So this is sort of like a modified, this is sort of like a modified Taylor series, actually, in some, except for these negative exponentials. There's negative n's here. But so this is, yeah, this is z to the n, basically. Not exactly z to the n, but very similar to z to the n. It's r to the n, e to the 2 pi inx. So this will be explored more in homework, this connection. But anyway, just thought I would throw that out there. Okay, so first of all, because this is a finite sum, you can interchange sums and limits, no problem. It's a finite sum, there's no issue there. So point-wise, for f and s, cf of x is given by this limit here. Now, the fact that we have an r here is going to make life so much easier for us in terms of summing things up and interchanging sums and integrals. Well, let's just see what I mean by that. So, well, let's just write the terms n equals 1 to infinity. Nothing there. And absolute value of n is n. Sine n is 1. F hat of n, well, these are the same. Okay. Now, if n is negative, so when n equals 0, this is 0. But when n is negative, so go minus infinity to minus 1, absolute value of n, maybe I'll make this a little smaller. Yeah, that's good. Perfect. Absolute value of n is minus n, so it's r to the minus n. Sine n is minus 1, so you got the minus here. We still got the f hat of n e to 2 pi I nx. Okay, so it's convenient to write this. So let me rewrite this real quick. Well, anyway, so pretend this arrow is here. So let's write this as n equals 1 to infinity. So this is going to be, well, it's just r to the n. F hat of minus n, e to the minus 2 pi I nx. So that means I can write this all in terms of one sum. And I can write f hat of n. Remember, it's going to be, or maybe let's not do that. Let's do this whole thing here. So it's 0 to 1, f of t, e to the, let me write it as, yeah, so I'll write it with a plus. Sorry about that. So it's 2 pi I. Well, here's x minus t, 2 pi I. Make that a little easier to fit in. So you get the minus t from this, the Fourier coefficient definition, and you combine that with this exponential here. And so this is basically going to be the same thing, except it's going to be a minus in front of it. It's going to be, instead of n, it's minus n. So you write this out. You get the following. Right? So again, this here is going to be the same thing as this, except for a minus n. But you still have the same Rn. Okay. And I just used Fubini's theorem, which is absolutely justified because, or rather interchange sums and integrals, because for fixed r between 0 and 1, both sums are uniformly convergent by Weierstrass-M test. Never mind there's a limit here. Fix r. Forget about this limit. Just pretend it doesn't exist. just fix R between 0 and 1. These sums are uniformly convergent. I can interchange sums and integrals, not a problem. Okay. And now the beauty here is for R between 0 and 1, this is a finite, this is a convergent geometric series. Without the R, you can't sum it. I mean, you can't. It just doesn't exist, really. Right, so, and right, how do you do this? Well, it's just pretty trivial. So if I want to, first of all, do one thing here. I'm basically going to add and subtract 1 when I write zeros here, because when n equals 0, this is 1. When n equals 0, this is 1. So basically, it's just 1 minus 1, and that's helpful. We're adding essentially 1 minus 1, which is 0, because now I can just use finite geometric series. This is 1 over 1 minus r e to the 2 pi I x minus t. 1 over 1 minus r e to the 2 pi I x minus t with a minus here. But this is the same thing as having a plus here and a complex conjugate. And whenever you have, in general, z plus z bar, this is 2i times the imaginary part of z. So pull out 2i, take the imaginary part of this, and not that it matters, but kind of I should extend these fraction signs, and trivially take the imaginary part, basically nothing to it. You're going to get r sine 2 pi t, 1 minus 2r cosine 2 pi t, plus r squared. And to make life a little easier, let's do two things. One, I'm going to basically do a substitution like we've done before. U is x minus t, or really x goes to x minus t. And because everything is is one periodic, that's just going to be the same thing as integrating over 0 to 1 when I do this u sub. You're really integrating from x minus 1 to x plus 1. Or rather, sorry, from x to you're integrating from x to x minus 1, or really x minus 1 to x after you have a minus sign pop out. But that, integrating over any interval of length 1 for a one periodic function gives you the same answer. So just rewrite it as 0 to 1. Well, actually, it's more easy to think of this as minus 1/2 to 1/2. Again, everything is one periodic, so no issue there. Okay, so now you might be tempted to say, well, okay, great. Maybe I can just interchange limits and integrals, and we're done. We have a nice form of this useful C function. Well, no, you can't do that. And the problem is, so basically pretend that R is not here. Or really pretend that this R is 1. So let's just say R is 1. So that this really is, when R equals 1, this is 2. Okay? Well, the issue here is that the numerator behaves for t close to 0. It behaves like t. The denominator behaves like t squared. So you really have a problem. You have a strong singularity, and you really can't use Fubini's theorem. Or, sorry, you can't do dominate convergence theorem to justify switching limits and integrals. You just can't, because there is no dominator. In modulus, this whole thing here for t near 0, and particularly for r very close to 1, behaves like 1 over t, and that's not a dominator. I mean, it's a dominator, but it's not an integrable dominator. So we need to be much more careful in what we do. All right, and it's not a hard fix, but it's a very useful fix. And you do this a lot in this in studying harmonic analysis, Fourier series, Fourier transform. Uh, so notice that working backwards, I'll leave this for an easy homework. This integral here is going to be 0. I don't want to say anything more. I really can't say anything more about this without telling you how to easily do it for homework. But so in particular, minus f of x times this here is 0. F is certainly a well-defined function. It's a linear combination of these complex exponentials. Okay. So I can trivially add 0 to this integral here. So I get that this is going to be this whole thing here. I don't want to bother writing 2 i's everywhere. So this whole thing here is going to be this integral. How does that help us? Well, you'll notice that I can multiply and divide by t as long as, well, t is not 0. So at least for almost every t except 0, I can do this. And you'll notice that, well, f is obviously differentiable. It's finite linear combination of complex exponentials. So this here is bounded for all t, not 0. And as t approaches 0, well, it's just a derivative at x, so it's bounded. So this is bounded, independent. This is uniformly bounded for all t not equal to 0. Well, this numerator now behaves like t squared for r very close to 1 and t very close to 0. The denominator behaves like t squared. So now you've essentially removed the singularity. Now you are justified, and not even just using dominated convergence theorem, but you can use the 511 bounded convergence theorem. And you are very safe in letting r go to 1 and interchanging integrals and limits so that you can literally let r be 1. So I'll leave it for a homework that the supremum here, so how do I want to write this? Yeah, t and this interval here, take away 0. So homework is at this here, and it's pretty easy. And you actually see expressions like this quite a bit when you study the Hardy space or the Bergman space. So it's good to do these like very, very elementary, almost like kind of laughably elementary kind of estimates. Again, particularly not even for this course, but if you want to do anything with any of us, studying the Hardy or Bergman space, Fock space, whatever. Right. So this here is bounded. It's finite. The supremum is finite. And the trick is all the trick is add and subtract in the denominator to r. But anyway. Okay, so right, so you get this here, and we can make this even more simple. I mean, this is almost like magically simple. We went from this horrific looking Fourier series definition of CF, and now we have this nice integral. So if you use a double angle formula, you get that this is going to be cotangent. Okay. And this is a pretty nasty, I mean, this is a fairly complicated operator because you can't just smash in absolute values to study this. You know, what's cotangent? Cotangent is cosine over sine. Took me a second to remember that. So sine pi t, when t is close to 0, that behaves like 1 over t, or that behaves like t. So you know, yeah, it has a singularity. that you have to deal with. I mean, the fact that we have a minus f of x, again, saves us because you can do that silly thing. You know, here it's probably even more transparent that t cotangent pi t is bounded as long as t, you know, uniformly bounded for t not equal to 0. And this is also, because it's just a derivative as t approaches 0, this is going to be, I guess just 1. Yeah, sorry, this is just, yeah, it's just going to be 1 as t approaches 0. Anyway, sorry about that. Okay, so you can alternatively write this, and this is probably, frankly, more useful. So what you can do is you can write this, and it kind of looks a little silly, but there's a very good reason why I want to do this. So there's really no issue with t equals 0, but I still want to write this as, let's write it as epsilon is less than absolute value of t is less than 1/2. Okay, so you can check. So this is literally just the integral sign. That's all I'm doing. So I'm not doing anything other than writing this integral as this limit, which trivially converges, even in the sense of Calc 1, or Calc 2 rather, improper integrals. As an improper Riemann integral, this exists. Okay, so you can also check, and this is key here, for any epsilon positive, and you absolutely need epsilon positive. This is literally Calc 1. Literally Calc 1. And you don't really need to do any, well, you really can't like play around with sums here because you don't have convergent sums. When you get rid of the r here, now you don't really can't go backwards and integrate an infinite sum because that infinite sum might not converge. But you don't need to. You can just look in a table to get the integral of cotangent. It's ln of sine t. I did have to look that up prior to making this lecture, but anyway, yeah, you can get that this is going to be 0. I can't stress this enough. For any epsilon positive, and you need epsilon positive. This is not going to make sense if you don't have an epsilon here. It's not really, the integral is not really defined because of the problematic singularity. Because the denominator here behaves like 1 over t as t is close to 0. But there's no issues here if epsilon is fixed. This is just a Riemann integral. This is a continuous function. Just take this integral, plop in epsilon, plop in 1/2, plop in minus 1/2, plop in minus epsilon, you get 0. Okay, so when you take this limit, this literally becomes, well, this here, and this term goes away, and you get what's typically called, sometimes there's the 2i here, you get what's typically called the Hilbert transform. Okay. So this is the Hilbert transform on the circle, essentially. And again, why do I, well, I don't know if I said this, but why do I say on the circle? Well, very trivially, you can take the circle, connect the two ends. Topologically, it's trivially a circle. I mean, just 0, 1, modulo, identify 0 and 1. That quotient space is just, you just pretend I take this pen. If it's Play-Doh, you just, wrap the ends around. Well, this is trivially homeomorphic to the unit circle. And I like using, probably notation Professor Zhu does. Yeah, and all you do is x goes to e to the 2 pi I x. Okay. Yeah, so 0 maps to the same thing that 1 does. It's just 1 on the unit circle. Yeah, so because of this identification, and trivially it goes backwards. 1 is identified to 0 is identified with, or 1 on the unit circle gets mapped to 0, which is the same thing as 1 under this identification. So anyway, yeah, because of this, we kind of think 0 to 1 periodic functions are the same thing as functions living on the circle, which is sometimes useful when you do party spaces, this thought. But anyway, yeah. So, yeah, like I said, I'll probably give homework on the connections between the Hardy space and what we're doing here. And frankly, that homework will probably come from Professor Zhu's book on the Hardy space, operator theory and function spaces.